So the strong nuclear force is the force that holds those opposite charged objects. Let's get back to helium. These two positive charges that really, really want to repel each other. It holds them together. So where does that force come from? Well, it's caused by these little tiny interactions between the protons, the neutrons, and things that make up those particles called quarks. Basically, here's a zoomed in picture. Um, what the thing that holds them together, they call gluons. Gluons are kind of like these tiny little springs or glue that hold these particles together. Now, it's not really sure, scientists aren't super certain what gluons are, but we can know their existence because it makes up part of the mass of the atoms. We can use the Large Hadron Collider to detect certain properties about them, but we'll talk more about that later. Let's get back to the field physics part of it. Um, so how strong are these gluons? Well, they have to be strong enough to overcome the repulsion forces. What are they? Well, they're basically particle interactions, like glue or springs that attach particles. And what are they made out of? Well, there's lots of different ideas, waves, light, energy, or other particles, maybe a combination of them. So we're not entirely sure, but we have ideas, and there's evidence for each one of those. So we'll talk more about that later. So let's look back at the 230 newtons of force needed to hold this next to this without it flying apart. Well, what else do we have in helium? Well, we have two protons, we have two neutrons, and we have some electrons that are really actually like really, really far away. And so this is not drawn to scale at all. So we're going to ignore those. So let's look into helium nucleus. So we talked about, well, there's two protons, two neutrons, and inside those protons and neutrons are quarks and gluons and other smaller particles. Okay, well, what is the mass of a gluon needed to hold a helium atom together? Well, what we can do is we can figure out how much energy is needed to hold the helium atom together, and that would be like the repulsion energy. Well, think about it. There's a repulsion force, there's got to be repulsion energy. Repulsion energy, which is equal to kQq over r. If you recall, it's just force times distance, so one of the r's gets canceled out. So plugging that in, this is how much repulsion energy is in every single helium atom. So the nuclear energy holding it together has to at least be this much. At least be this much. So what we can do is we can use good old E equals mc squared, which is the equation for nuclear energy, and plug in this for the nuclear energy. And rearrange it to solve for mass. C is the constant, which is the speed of light. So the mass would equal the nuclear energy divided by speed of light squared, which gives us a value of 2.5 times 10 to the minus 30 kilograms. So the mass of a gluon, this particular gluon, is 2.5 times 10 to the minus 30 kilograms. So that's really small. Not much matter is needed to hold helium together. If you recall, the mass of an electron is about 9.11 times 10 to the minus 31 kilograms. So roughly about 2 or 3 electrons would hold this entire nucleus together. Obviously, the electrons have charges, and the nucleus has a charge, but even it's not electrons that are doing this, it's other particles. It's these gluons. What are these gluons made out of? Well, leptons. That's one idea, is leptons. We can detect these leptons. Most gluons are made up of leptons, and leptons are just a group of smaller particles that are very, 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 very small, but they have distinct properties. Let's go over what leptons, or different types of leptons are. So leptons are just basically a classification of particles. We know of one in very good detail, electrons. Electron is a classification of lepton. Leptons are just very, very small particles that have either positive charge or negative charge, and you can have matter leptons and antimatter leptons. So we'll talk about that too. But there are other leptons too. Muons are slightly heavier electrons, basically. And then tau electrons or tau leptons are very similar to electrons and muons. There's neutrinos, which are basically like, well, they're kind of like electrons, but they don't have any charges. There's different types of neutrinos too, different sizes.